Well, we know this because there are tests that can be done. Y'all ever seen somebody have to use one of those? Okay. Oh, man. That is so interesting. The way that we measure the function, spirometry. This is how we're going to test someone's ability. Basically, the pulmonary ventilation, we get to assess it. Now, this could be done based on diseases that that person might have, but what's another time that they use these? After surgery, okay? After a surgery that, especially if somebody's been put to sleep for a long time, okay? Like if they've been under for a really long time, they're going to do this with the person. We want to see if whatever's taking place with their ventilation, is it improving or not? So the spirometer recaptures the expired breath because they breathe out into it. Based on the information that you learn to use this, they do some math, and then there's a norm that people fall into. The norm is not the same across the board because our lung function changes as we get older, okay? Lung function changes based on any diseases that might be present. Now, the volumes that your textbook is going to go into great detail about, it's going to talk about a tidal volume, inspiratory reserve volume, expiratory, and residual. This is just simply the way that they measure what they find on that respirometer. And then what they determine based on tests that can be done. I am not asking you all to remember this, okay? If you're going into respiratory therapy, trust me, you're going to see this right here. It's math. That's all it is. You take the numbers, plug them in, and you do the math. That's it. It's not anything difficult. I just don't see a need for us to get into it. Okay? So, they'll actually take their numbers, plug them in, and they'll get what's called total lung capacity. And this is what they'll use in terms of someone they may be treating with respiratory problems. Okay? Not asking you all to remember that. The disorders that are going to affect the lungs, we can either have restrictive disorders or obstructive. Restrictive, obstructive. Restrictive disorders, they reduce the pulmonary compliance, limit the inflation of the lungs. When they're doing tests, it shows up in one of those numbers. An example of a restrictive disorder, black lung disease. Ever heard of that? Okay, it's what the coal miners get. All right. TB, tuberculosis, which is on the rise again. Don't know if you guys know that. We thought we'd pretty much gotten rid of that, but you never really totally eradicate anything. Okay. Now it's making a comeback. What's the problem now, though? Is tuberculosis bacterial or viral? Bacterial. Okay. What's the problem we're facing now? We're finding it be resistant. Why?
Yeah.
Go ahead, Cass. Too many antibiotics. Too many antibiotics based on what? Well, people taking them when they don't need them. And then not finishing them when they get them. And what else? Worst stuff ever. Worst stuff ever. These are going to make it harder to breathe. They're going to affect the lung tissue and make it harder to breathe. Obstructive disorders. Something interferes with our airflow, blocking or narrowing the airway. Asthma. What happens when someone has an asthma attack? They're going to basically constrict up in their bronchioles, and it's like they won't open back up. That's why the person feels like they're kind of maybe smothering or something and having that attack. They have to, depending on the severity of it, they might need to have to keep an inhaler with them, okay? Or they have an inhaler that they use daily, okay? It's a dilator. They're called bronchodilators. Chronic bronchitis. What does that tell me? Inflammation is present. This one, once again, tested for by the spirometry, and basically how much air can be exhaled at a given point in time. In your textbook, there are different, they give a list that will affect, and basically the restrictive and obstructive disorders that we have. Now, when we begin to look at the respiratory system, the composition of the air around us will affect or have a play on my respiration. Why?
The air you're breathing in has too much carbon dioxide and less oxygen than you can absorb the air. Like, there's not enough air to actually get the alveoli that to absorb the oxygen and for efficient gas emission. Or if you have too much oxygen.
Well, sort of. Atmospheric pressure.
Sea level.
We're at sea level. Kaz, where are you talking about? Mile High City. Breckenridge. Vail. Probably the highest I went was Vail. And actually had to stop the car. I mean, I've been in college, because you go and you got to kind of let yourself acclimate for a couple of days. Thought I had acclimated okay. Take off to go up to Vail, and I don't know, 18,000 feet maybe? I'm like, I can't breathe. Why? Because I'm at what level here? I'm at sea level here. My atmospheric pressures are different. Those atmospheric pressures are going to play on what happens with my breathing that occurs. Okay? And then, not only do I have to deal with that, but you have to make sure that you can compensate with the red blood cells. So for me to go from here to Mile High City, okay, you need to give yourself about 3 days to acclimate. You need to drink plenty of water, because guess what your body's doing? It is stimulating erythropoietin production. And erythropoietin is affecting what? My red blood cell production, because I need more of them than what I need here at sea level. So our external environment affects our respiration, our gas exchange, okay? Because in Mile High City, I need more oxygen. And the body needs to produce that, the red blood cells to carry it. Now, gas laws, don't forget them, okay? Now, in the gas exchange, Dalton's, because Dalton tells us, and remember, if it's a law, it can't be changed, okay? Dalton tells us the total atmospheric pressure is the sum, whoops, that should be of the contributions of each individual gas. So my carbon, my oxygen. Because I have more than one gas, each gas has a partial pressure. Oxygen will have a certain amount, CO2 will have a certain amount. They're in a mixture. Think about that for a second. These pressures are based on my altitude. At this level, oxygen's pressure would not be as great as at Mile High. I gotta have more at Mile High than I do here at sea level. But I also got my CO2. So I've got pressures of each one, and together they give me the sum. Math, you guys. Straight up math. The air that we take in is not going to be the same composition as what we find in the grapes. What? What does that tell me? I've got my dead spaces. I've got the air that I'm going to breathe in, but at the alveoli, I'll have an oxygen and CO2 count that doesn't match what's out here around me. Does that make sense? So when we get to the alveoli, when we're at the structure of my grape, all right, and then that grape is in connection with all those capillaries. Remember, their basement membranes made up the respiratory membrane. Is everybody with me so far? And there is a fluid present. So that tells me water is present. Right, because the fluid and cells and extracellular fluid in this membrane, we're going to have a layer of water. Now, that's kind of important. Because what I'm trying to get to happen is O2 to move this way and CO2 to move that way. If the gases could not dissolve in water, I would be in trouble. But we know CO2 dissolves in water because it's put into soda. Okay? I know oxygen dissolves in water because you can pump it through the water. Water is an oxygen, H2O. So, what becomes important is for the dissolution to occur. We need those gases to dissolve so that they can cross this membrane, and then for it to go from the blood into the lungs. The term for this exchange is alveolar gas exchange because we're at the level of the grape. They want to move down their concentration gradient. So they want to go from the area of high concentration to low concentration. So if oxygen is high in my alveoli, low in my blood, it wants to move in that direction. If the CO2 is high in the blood, low in the alveoli, it wants to move in that direction. Now, Henry tells us that at a constant temperature, what does that mean? What's our body temperature? 98.6. At the constant temperature, the amount of gas at any time and the volume is proportional to the pressures. So pressure is going to affect the movement of these gases.
So your pressure is off, which will be off.
Yes, your pH will be off. Then your body is going to kick in the either increasing or the decreasing of your respiration to balance out the pH of the blood. When we look at the exchange that takes place, oxygen, CO2, pressure not only inside the lungs, inside the alveoli, okay, and the pressure that's around us, they are going to affect the movement of the oxygen and the CO2. A hyperbaric chamber. Ever heard of these? Okay. When are they usually used? For example,
One function is really decreased, or like how much.
say for example, you go scuba dive. Come up too quick. What happens? The bends. Ain't a whole lot of fun, is it? I know I wouldn't want it. Okay? I've seen shows on it. Okay? They can put the person in the hyperbaric chamber and get rid of the gas bubbles in the blood. And it'll cure it. Hopefully, it'll take care of it. So what we'll do, hyperbaric chambers are for affecting the oxygen in the blood. They're used in different cases, different situations where maybe lung function, like I follow, bless his heart,